Today we're going to be talking about how to find the equation of the tangent plane and also the symmetric equations of the normal line to the given surface. And in this particular problem, we've been given the surface 2 times the quantity x minus 2 squared plus the quantity y minus 1 squared plus the quantity z minus 3 squared is equal to 10, and we've been asked to find the tangent plane and the normal line to that surface at the point 3, 3, 5. Now, as a reminder, I've written the formula for the equation of the tangent plane. What we need to realize about this formula is that there's really just 3 components to it. We have our first component here, which is the partial derivative of f with respect to x, evaluated at the point x sub 0, y sub 0, z sub 0. And this x sub 0, y sub 0, z sub 0 point is the point we've been given, 3, 3, 5. So essentially what we're going to be doing here is taking the partial derivative with respect to x and evaluating it at that given point. Then we're going to take the partial derivative with respect to y and evaluate it at the given point. Then we're going to take the partial derivative with respect to z and evaluate it at the given point. That's going to give us, as you can see, the vast majority of our formula. All that's left are these 3 pieces here, x minus x sub 0, y minus y sub 0, and z minus z sub 0. And all we're going to do is take our point 3, 3, 5 and plug those values in for x sub 0, y sub 0, and z sub 0. So here, here, and here. And all we're going to be left with of our original formula is this x, y, and z value that we have in the formula. We're going to set this whole thing equal to 0, and that's going to be the equation of our tangent plane. And then from there, it'll be easy for us to find the symmetric equations of the normal line. Now keep in mind here that the tangent plane that we're finding is the surface or the plane which is tangent to this equation. Now this is the multivariable version of the equation of the tangent line, which we found as being tangent to some function in an xy coordinate plane when we were dealing with just single variable calculus. So where before we had some function like this, let's say like this, and then we had to find the tangent line to this equation at this point, and we calculated the equation of this line. That was in single variable calculus. In multivariable calculus, we have, instead of a 2-dimensional function like this, we have a 3-dimensional function, and this line becomes a plane. So the tangent plane, the plane that barely skims the surface here of this equation, this function, and intercepts this function at only the given point, 3, 3, 5. So let's go ahead and get to calculating it. Again, we're just going to be finding first order partial derivatives of this function. So we'll go ahead and find the partial derivative of the function f with respect to x, and then we'll evaluate it at the given point. So with respect to x here, remember that means that we're treating y and z as constants, taking the derivative with respect to the variable x. So for this first term, 2 times the quantity x minus 2 squared, we're just going to use power rule with chain rule. We're going to bring this 2 exponent here down in front and multiply it by the coefficient, which is 2. So 2 times 2 is going to give us 4. So we'll have 4. And because we're using chain rule, we're going to leave our inner function, x minus 2, completely untouched. So x minus 2, we're leaving that alone. And according to power rule, we subtract 1 from the exponent. 2 minus 1 gives us 1. So we're just going to put a 1 here, but that's redundant. We don't need to write it. So we just have x minus 2 to the first power. Now, according to chain rule, we have to multiply by the derivative of this inside function. We have to multiply by the derivative of x minus 2. Well, the derivative of x minus 2 is just 1, because the derivative of x is 1, the derivative of negative 2 is 0, so we get 1 minus 0, or just 1. So we don't have to actually write that down. Multiplying by 1 won't change anything. So here's our partial derivative with respect to x. Now what we want to do is evaluate that partial derivative at the point 3, 3, 5, the point that we were given. So what we'll say is the partial derivative of f with respect to x at the point 3, 3, 5 is equal to, and here's where we plug in, so we get 4 times x minus 2. X in our point here, the value of x is 3, so we get 3 minus 2. This is equal to 4 times 1, or just 4. So that's how we're going to find each of these values. Let's go ahead and take the partial derivative of f with respect to y. And again, here we're treating x and z as constants, taking the derivative with respect to y. Now, one thing we didn't cover in the last partial derivative, we took the derivative with respect to this term, but we ignored the rest of the equation, and that was because we were treating y and z as constants. The derivative of y minus 1 squared with respect to x is just 0. There's no x variable involved in this term, so its derivative is 0. Same thing with the quantity z minus 3 squared and 10. The derivative of each one of those is 0, which is why we're just left with the derivative of 2 times the quantity x minus 2 squared. Similarly here with the partial derivative with respect to y, the derivative of this first term, which only involves the x variable, will be 0 because we're treating x as a constant. The derivative of z minus 3 squared is going to be 0, and the derivative of 10 will be 0. So we really only have to pay attention to this term here, the quantity of y minus 1 squared. So again, power rule with chain rule, we bring the exponent down in front and we get 2 times y minus 1. We ignore that inner function. Subtract 1 from the exponent, 2 minus 1 gives us 1 for our new exponent. And then we have to multiply by the derivative of the inside function according to chain rule. But the derivative of y minus 1 is just 1, so it's redundant really to multiply this by 1. We don't actually have to write that down. Now we evaluate this partial derivative of y with respect to y at the point 3, 3, 5. And what we get is 2 times, here we have y, the value of y in our point is also 3, so we get 3 minus 1. That's going to give us 2 times 2, or just a value of 4. So our third step, of course, is to take the partial derivative with respect to z. And again, the derivative of each of the other terms will be 0. The derivative of the quantity z minus 3 squared will take in the same way, and we'll get 2 times z minus 3 raised to the first power. We multiply by 1 according to chain rule, but we don't have to write that. And then when we evaluate the partial derivative of f with respect to z at the point 3, 3, 5, what we end up with is 2 times the value of z in our point is 5 here. So we get 5 minus 3. That's going to give us 2 times 2, or just 4. Okay, so we found each of these values here, each of the partial derivatives evaluated at the given point. So now we can find the equation of the tangent plane. The equation of the tangent plane is going to be our partial derivative with respect to x evaluated at the given point, which we know here is 4. So we're going to get 4 times x minus x sub 0. So we're going to leave the x sub 0 we're going to get from our given point, and the value of x in our given point is 3. So we'll get x minus 3. Then we're going to add to that the partial derivative with respect to y evaluated at the given point, which we found was 4. So we'll say plus 4 times y minus y sub 0, which we take from our given point, and the value of y in the given point is 3. So we plug 3 in, then we add to that the partial derivative with respect to z at the given point, which we know is also 4. So we get 4 times z minus z sub 0. Well, the value of z in our given point is 5, so we get z minus 5, and we're going to set that equal to 0. That's the equation of the tangent plane, set it equal to 0. Now we could leave it like this, but it's helpful to multiply through here, expand these polynomial terms to see if we can simplify any further. So if we multiply 4, if we distribute the 4 across the x minus 3, we'll get 4x minus 12. If we distribute the 4 across the y minus 3, we'll get plus 4y minus 12. Distribute the 4 across the z minus 5, we get plus 4z minus 20 is equal to 0. When we simplify here, we get 4x plus 4y plus 4z, and then we have minus 12 is minus 24. Minus 20 is a negative 44. If we add that negative 44 to both sides, it'll cancel on the left-hand side and we'll be left with positive 44 on the right-hand side. And here's why we simplify, because now, as you can see, we have a simpler form of the equation of the tangent plane. All we want to do now is divide through by 4, so that what we're left with here is just x plus y plus z is equal to 11, and that's a much simpler equation for the tangent plane than our first equation, which we had here. So this is the equation of the tangent plane. That's our final answer for that. Now we want to find the symmetric equations of the normal line. Well, that's going to be really easy to do when we already have the equation of the tangent plane. All we do is we go back to our original equation of the tangent plane, which we had here, And we're going to take these three pieces. We're going to take x minus 3, y minus 3, and z minus 5. We're going to ignore the coefficients and ignore what we have over here on the right-hand side. These pieces are the only things that we're interested in. And here's how you write the symmetric equations of the normal line. You're going to say x minus 3, that first component there, x minus 3, and then you're going to divide that by the partial derivative of f with respect to x evaluated at the given point, which we already found here was 4. So we divide that by 4, and then we set that equal to the same thing that we get when we do this same process for y. So y minus 3 from the equation of the tangent plane divided by the partial derivative with respect to y at the given point. So that's 4. And we're going to set that equal to the same thing for z. So we're going to get z minus 5 over, again, 4 because we already found that value. These are the symmetric equations of the normal line. In this particular problem, we can go ahead and simplify because each of these are over 4. We can reduce this equation multiplying through by 4, and what we get is x minus 3 is equal to y minus 3 is equal to z minus 5. Not often will your denominators always be the same, and so you won't necessarily be able to do that, but in this particular case, we can. So that means that this here is our final answer for the equation of the tangent plane, and this is our final answer for the symmetric equations of the normal line.